All right, so we are going to begin chapter 7. Of course, beginning with section 7.1. And we get to talk about radicals. Radicals. It's okay, you can say, oh, that's like so rad. Because I know you're like compelled to say stuff like that. Yeah, no. No. If you did, I'd kick you out of the class anyway. That's like really 80s. And even though it was like popular to say, I never said rad. I don't know. I'm so glad I didn't, because that would have stuck with me for a long time. So we're talking about radicals and exponents to begin the class. So whenever you hear radicals, what do you think of? Doesn't even matter. You hear the word radical, what do you think of? What's that?
The Revolutionary War.
The Revolutionary War.
The radicals in there.
Hey, there you go.
About that in history. Yeah.
Which is interesting. Okay. What else might you think of? Why were they called the radicals?
Because they were...
Radical?
Yeah.
Yeah. Go figure.
What they were doing. They were really intense. Like, yep.
Well, we're going to be looking at stuff that is intense or radical, but we'll look at it in a mathematical way, which is the best way you can ever look at something radical, right? So whenever you think of, and you may or may not know this, but whenever you think of radical, what type of symbol do you think of? Mm-hmm. Right. The square root sign like this. It looks like a division sign, but it has this little V out to the left. And then we're also going to talk about exponents and how they correlate with radicals. Whenever you think of an exponent, what do you think of?
The little number above something.
The little number above something. And that is really the mathematical definition of an exponent, is the little number above something. So that number right up there is the exponent. So we're going to talk about what these have to do with each other, when in fact they actually have a lot to do with each other. They play off of each other quite a bit, and then we're going to see how, why, and then ways that we can manipulate it. First of all, the exponent is the superscript. You'll hear superscript and subscript. Super means upper, sub means down below. So sometimes we have to put numbers at the bottom of a base to explain something. This would be a subscript. But an exponent is a superscript, so it's an upper number to a base.
What do you call the bottom one?
A subscript. S-U-B. Now we won't be using them very much, like at all, but you may hear the term, or if you have an app, or you end up using your laptop or something and you can mess around with them and put numbers up high or down below. The subscript is what goes down below, and then the superscript is the number up top. The exponent is a superscript written after a term or a base, indicating the number of times the base is to be used as a factor. So if we were to factor this out, x to the third, we would have x times x times x. So basically, you're going to multiply that base out, and you're going to list it this many times. It's kind of like talking to a little kid. How old are you? I'm this many. And so this x is saying I'm this many. I'm 3. So you'll see them factored out in 3 times. And that's all that really means. But why that part is so important is how it ends up relating to radicals. Because these radicals are basically telling us how we're going to play a game, or how we're going to distribute our teams. How many people can be on a particular team. And if we don't have a whole team, well then too bad. Sometimes we even relate it to, if you think of any type of group activity that takes place. It can be a dance, it can be a game, it could be a class that's put together, it could be teams for sports events, however it helps you to think of then envision some real life situation that we'll be talking about. So let's look at page 266. 266. We're going to review this. We should be familiar with this already, but now we're going to look at it inside the book. We're going to look at properties of exponents. Properties of exponents. So what we're going to be talking about is we have A and B that are essentially going to be our superscripts, our exponents. And then we're talking about all real numbers where x cannot equal 0. All right, our base cannot equal 0. So that's the definition. Those are the parameters of what we're going to be dealing with. So it gives us everything but x equaling 0. The product property is whenever you have an exponent, or if you have a base with an exponent times that same base with an exponent. Well, what do we do with those exponents when we're multiplying? We add them. We add the exponents when we're multiplying the bases. When we divide the bases, what do? We subtract. We do the opposite of what happens whenever we multiply. Then whenever we have a quotient property, and this means whenever you have x to the exponent of a, and that is all encased with an exponent of b, well then what do you do with these exponents here to figure out what x will end up being, the new exponent for it? Do y'all remember? Well, we add when we're multiplying. So if we add x to the third times x to the second, we will add those. 3 plus 2.
Wouldn't you times them? Well, it's because you're telling the a to times itself by whatever it is.
Absolutely. So if this were 4 and this were 5, well, we are going to take x to the fourth and multiply that out 5 times. So we'll have x to the fourth times 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 x to the fourth. Okay, 1, 2, 3, 4, 5. Factored out 5 times. And if you think about it, we can add 4 5 times, or we can multiply 4 times 5. Either way, you're going to get the same thing. But so here, whenever we see, and the big hint is the parentheses, because it's saying this whole term here is to be factored out 5 times and multiplied together. In which case now we know that if we're multiplying exponents, we simply add them, which is the same as multiplying. We end up with x to the 20th. Okay, and so that is our quotient property. I'm sorry, our power property. Then we have our 0 property. What is x to the power of 0? Without looking at your book, some of you already looked, but what is x to the power or to the exponent of 0? It is 1. Anything with an exponent of 0 is uno. There, you had your Spanish for the day. So it is 1. A negative exponent. A negative exponent. Can we have a negative exponent? No. Everybody shake your head. No. No, we cannot. If you try to calculate it, your calculator will show up as an error. So if you have x to the minus 2 and try to calculate it, it won't work. So what do we do with it? Anybody know? No, good guess though. We will, but we got to do something first. Well, not square root it. We will square it, but we got to do something first. This will be squared, but we have to do something. What do you think we have to do? Now you can look at your book, and it'll tell you what to do. That's the easy way. You can look at me, but somehow be able to read your book while you're looking at me, and that way you can cheat, but I can't tell, and then you look really, really smart when you give me the right answer. So that's always possible. So what we do, anytime you see a negative exponent, that means that we're going to take the inverse of what this is. So the inverse of x is going to be 1 over x, and then we keep the same exponent, but that's where we remove the negative sign from the exponent. Make sense? So what if it were 1 over x to the negative second? What would that be? Well, think about it. If we had this, x to the negative 2, and in order to get rid of that negative, we have to take the inverse.
Over 1 again? Or inverse it again?
Yeah, we just inverse this.
Let's see if I can.
So then it would just be x squared. We take the inverse, and remember, x over 1 is the same thing as just x. And then we keep the same exponent, but the negative sign is removed once we take the inverse. So if you see something like this with a negative exponent, you're like, oh, I can't do that. I'm not allowed to do that. So I have to take the inverse of what that is, and everything else about that will stay the same except you get to remove the negative sign. And that we can do. You can plug in 1 divided by something squared and come up with an answer. Make sense? All right. Then we have the power of a product property. And what this means is, in your book it uses A and B, but if we have x times y, and that is to the power of 4, then that power applies, or that exponent applies to every element inside this parentheses. So this will actually be x to the 4th times y to the 4th. Or if we had 2xy, then it would be 2x to the 4th, y to the 4th. Does that make sense? Sorry if that was like that.
And then wouldn't it be 2 times 4?
You were almost so close and so right.
2 to the 4.
Yes,
Yeah,
very, very
right,
good.
yeah.
And this is a common mistake. You will see somebody do this. Well, it would be one of 2 mistakes that'll take place. Either their brain is so fixed on these variables that they will just put the 2 down and then x to the 4th, y to the 4th, or they will do 2 times 4 and it'll be 8 x to the 4th, y to the 4th. Which is interesting because you're taking these to the power of 4, then why would you multiply that out? A lot of the times is that's just how your brain is working because you're moving fast. Sometimes it's necessary to stop, take a step back. Does this make sense? What I just wrote down. On your SAT test, you will most likely see answers similar to this as possible answers because they are common mistakes from people. So you are absolutely correct. The right way, so these are bad, don't do those. Good to recognize them, but don't do them. The correct answer will be 2 to the 4th, x to the 4th, y to the 4th. And then of course we can simplify 2 to the 4th being 16. 2 times 2 times 2 times 2. Can we simplify x to the 4th, y to the 4th? Can we simplify that any? Nope, there's nothing else to do with it until we find out what the values for those are. Does that make sense so far? Awesome. So that is the power of a product property, and then we have a power of a quotient property. Power of a quotient. Now, whenever you hear the word quotient, then you should be thinking of dividing, okay? Or you're going to think of maybe ratio. It's going to be most likely some sort of fraction form. So if we have A over B to the 6th, just like what we were just talking about, this will end up being A to the 6th over B to the 6th, because this exponent applies to all elements inside the parentheses. Easy enough? Cool. Well, understanding these concepts and remembering them is going to be very, very helpful, especially in section 1, but especially also as we go throughout. So if you need to, if you see something, you're like, okay, I think I know what this is, but I don't quite remember, go back to this table on page 266, and it gives you the examples of what to do with those. It'll be very helpful. Okay, the next definition is a rational exponent. A rational exponent. So here we have basically whenever you, I don't know if y'all remember this, whenever you think of a rational number, what type of number would you think of? Like, throw out a rational number. Any rational number that comes to mind. They were like, I don't know. What's rational? Irrational. My brother's irrational. Rational number. Do you think of the Venn diagram that was listed with real numbers, whole numbers, integers, irrational numbers, rational numbers? What are the first 5 letters of rational? What is it? R. There's an A. T. R-A-T-I-O. Ratio. First 5 letters of rational, right? Well, a ratio is a comparison. So what type of number would you think of that is a comparison? In what form? Would it be a whole number, decimal number? Fraction. Yes, fraction. Very good. It's a fraction. So like 3/4 is a ratio, comparing 3 to 4. Okay, so if you hear quotient, we went down a rabbit trail. If you hear or read quotient, go ahead and begin thinking fraction. Okay, because we're talking about ratios and comparisons, so think of fractions. So what we're going to be talking about here is if you have x to the power of a over b. X to the power of a over b. Now, this part is just going to require memorization. So I suggest you write this down, write arrows, make it in different colors, whatever helps your brain remember this. Once you memorize it, it's easy. It's really easy, and it's not really hard to begin with. But you can mix it up and end up with wrong answers. So, and you can look at your definition if you want to, but we'll write it up here. This, another way to rewrite this, you will have our base. The exponent to that is going to be the numerator. And then this is going to be turned into a ratio. We'll have a radical sign. I'm sorry, I didn't mean ratio, I meant radical. A radical sign. And then this part right here is where the denominator goes. Do you know what that part of the radical is? Anybody remember the name of it? I'd be really impressed if y'all remember. Index. Very good, it's an index. That's awesome. The index is what this is right there. Honestly, whenever I was in high school, I would have never remembered that. So, don't feel bad. So, if we need to rewrite this, we have our base with a fraction. We simply write our base. The numerator is going to be the exponent. We put it under a radical sign. And this part right here, the index, is going to be the denominator. Okay? Makes sense? So that is a rational exponent. Rational exponent. Now in this situation, notice that there are more parameters that are set within the definition. It says where x is greater than 0. It's still not equal to 0, but now it can't be a negative number. It has to be a positive number. And a and b are integers where b cannot be 0. So look at the example. Why can't b be 0? bb. Why can't b be 0? Why can't the denominator be 0, most importantly? Can you divide something by 0? Nope, stick it in a calculator, see what happens. You'll get an error sign. So, we have our parameters, and what's interesting is, before you start going and doing a whole bunch of work, understand the definitions and see, is this problem workable? So if this is a negative sign, if x ends up being equals, this is 2, and it's negative 4 to the 5th, well, already we're going to have some problems, and we can recognize that. Okay, and we'll see why here in just a little bit, but simply recognizing that you cannot have a negative here. This part, the denominator, and again, this would actually be written as -1 with 5 over 2. Translated to this, I'm sorry, 4. Translated to this. Or if you had positive 4, 5 to the power of 5 over 0, then you know we're going to have some problems. And so you can just stop right there. Cool, makes sense? All right, so let's do this. Well, we need to go over the properties of powers and roots on page 267. Let's go over these, understand what we're dealing with, and then we'll go through some examples and see how these actually work. So we have products and we have quotients. Products means we're multiplying, quotients mean we're dividing. So we have powers and roots. So if we saw this, x and y was to the power of a, then this would end up equaling x to the a, y to the a. Likewise, if we had x times y with the index of a, that's going to be the same thing as this. Okay? Your index stays the same, and all you do is combine what's underneath the radical sign. And you can go back and forth. Now this is important because sometimes we need to rename what we have so it makes it easier for us. Okay? Just like you may have to rename a sibling just to deal with it. You should try it sometime. Just out of the blue, rename your brother or sister, start calling them by a completely different name, and see what happens. It makes your life easier. It could end up being kind of difficult on them, in which case, if you cause them to sin, then you got to ask for forgiveness and stop doing it, right? Yes. And mean it, by the way. Okay, so then we have our quotients. So if we have this, x over y, both of those to the power of a, well then that equals x over a over y over a. Likewise, if we have the same thing, where we have this, oh, I'm sorry, nope, that is wrong. I was jumping ahead. This. You have a radical of x over y with the index of a. If you have this, then that is the same thing as that. Make sense? So you have, they're both sharing a radical, or you can split it up and have their own individual radicals. Okay, so know that we can move back and forth. Did you have a question?
No.
You sure?
Yeah.
Okay. All right, so we'll see more of this. Let's actually apply some examples to these and see how we move them back and forth. It'll actually be pretty easy. What is important, though, is these are one of these concepts that you can pick up really fast, you can end up doing really fast, and you can really make a whole bunch of mistakes because you're going too fast. Okay? So it's like adding 5 or 6 numbers in your head, and because you think you know how to, but then you end up making mistakes. So let's do this. We'll start with example number 1. We're going to write this. In exponential form. So we have radical form, which is this, because the radical is being used, the radical sign. We are now going to change it to exponential form, which is exponent form. So then we will see the radical sign gone and everything in exponents. You'll just have base and exponents. Okay? So, whenever we were originally going from exponent to radical form, what ended up being the index whenever we had a fraction as the exponent? Was it the numerator or the denominator that was the index? The denominator, okay? So, starting off with that is going to help us a lot. All these were the numerators, but that was the denominator. So we know that each term is going to have its own exponent in fraction form. And we're going to do this one at a time. So we have 25. And what is 25's exponent right now? Just the 25 inside here. 1. Whenever you don't see an exponent, that means it's understood that there's a 1 there. And that 1 is going to be in the numerator, and then our index is the denominator. Then we will go to our a. That is to the power of 3. That is our numerator. The 4 stays the denominator. And then finally b. Again, we don't see an exponent, so it's understood to be 1. So then that would be 1 over 4. So here is exponential form. And radical. And you can go back and forth. Yes?
If you change that to 2/4, you can make that 5 instead of 25, right?
Yes, you could do 5. This could be renamed as 5 and to the power of 2. So it would be 5 to the 2/4. Is that what you're saying?
Mm-hmm.
Yes.
Or 5 to the half, wouldn't that be that?
Huh?
Could
Or
you do
5 to, that's actually a good question. We will see and hold on to that. Okay? Can you simplify a radical? An exponent. Can you simplify an exponent?
Why not?
Good question. And we will see. Let's focus on getting these down, but I'm glad you're thinking like that, because that's really good. Anytime you say, what can I do more with this, and try to figure it out, will help you in the long run, because that's problem solving. All right, so everybody has this down? Let's do another one. Just think, probably 8 minutes ago you were like, what? And already you're like, oh, okay, I get this. This is easy. Not hard, right? So let's do this. Okay, this is in what form?
Exponential.
Exponential, very good. Let's change it to radical form. How are we going to do that? Radical form means that we have a radical sign. We look at our denominator. They are all the same denominator. We have a common denominator in the exponent. That helps us. If we don't have that, that causes some issues. We just have to do things differently. But here, we can go ahead and put that in the index. And then we can rewrite these with our each base with our numerator as the exponent. So a 3, x to the 5th, y to the 2nd. Everybody get there? Cool. Any questions with that so far? That is all that we'll do on this one, on section 7.1. We'll stop there. Let's move on to 7.2. 7.2. Here we are going to simplify expressions. Simplify expressions. I will read here off of page 274 in the middle of the page. Simplification of radicals depends on the expression under the radical sign, called the radicand. Okay? The expression under the radical sign, or contained within the radical sign, is called the radicand. You must simplify a radical expression if the radicand is one of three things. Is an exact power of the index, a square root of a square, a cube root of a cube, etc., or contains a factor that is an exact power, is in a fraction, or 3 is in the denominator of a fraction. We'll go over what these are here in just a second. We're going to look at each of the examples that we have for this. So, what does all that mean? Can anybody explain that better? Shake your heads from side to side. Nah, not really, because we are more visual people. We like to do hands-on. We need to see it shown. Reading something in mathematical terms doesn't really help us out that much. Sometimes it does, we kind of get it, which is why whenever we do word problems, it's important that we draw out and write out what it is that it is telling us, because we can visually see what's taking place. Reading a word problem is difficult. Same thing with our definitions. So let's look at example number 1. We are going to simplify this. Now, what's interesting, let's talk about this index first before we carry on. This index, or this number here, tells us how many of a term factored you must have on a team in order to come out and play. Right now they're on the sidelines or sitting on the bench, or however you want to envision this area under the radical. The radicand is this area here, but think of this as the bench. In order to go out on the field, this tells you how many people you must have, or how many factors of each of those elements you must have for you to come out as one team. Okay, for example, let's look at a bit more simpler. You have to have 3 A's to come out as one team. So we can simplify this as 360. Now, we have 5. If we bring out 3, how many are we going to have left over? 2. So we'll have a squared, b to the 7th, but we have one team of 3 that's able to come out, and they are one team. Okay, this is the trickiest part. A lot of times people will bring out and they'll say a to the 3rd. It's not a to the 3rd. Okay, it was a to the 3rd in here. Another way to think about this, and let's just look at the A's. We have a times a times a times a times a to the 5th. You have to have 3 in order to come out. Well, we're going to take these 3 right here, and they're going to be a team, and that team gets to go out onto the radical, or out of the radical, off the bench and out in front as one team. Does that make sense? Yes, no, maybe so? Okay, so make sure that you get that. Now, whatever's left over stays here. Now, what's interesting is we have a to the 2nd. Well, this index says you must have 3 in order to have another A team come out. We only have 2. So, tough luck, you don't get to play the game, you're stuck on the bench. But there's plenty of water and juice packs to go around, so you can just hang out there until the game is done. But it's still kind of boring, but whatever. but they cannot come out and play. All right, so now, understanding that, let's work on b. Okay, we have b to the 7th. How many teams of b can come out? 2. Who said 1?
Nobody said it.
I was about to say. Very good. It's 2. You get to have 2 B teams. Okay? Now this is what's interesting, is it will be B squared. B squared. You have a B team, and then times another B team that gets to come out. So we have 2 B teams that get to come out. Let me write it out just like I did with the A's, so it'll be a little bit more clear. We have B times B times B times B times B times B times B. 1, 2, 3, 4, 5, 6, 7. The index says we must have 3. 1, 2, 3, that's 1 B team. 1, 2, 3, that's another B team. Now those B teams, okay, whenever we're counting them together, they're actually multiplied, so we end up with B squared outside. So we're able to pull 1 team of A out, 2 teams of B, so we have B squared. And how many were left over of the B's? 1, so that exponent stays just like it is. Now we have the 360 to consider, because we can't forget the whole number. We started off with the letters because those are easier to see. So now let's apply what we've learned with the 360. The best way to do that is to factor it. So we have, anybody want to help with this factoring? What do we have? Let's start off with 36 and 10. 36 and 10. So now we're going to create a tree with all sorts of branches. This will be kind of cool. 10 is 2 and 5, that's easy. And then whenever we're done to our prime numbers, let's circle our leaves so that we don't get them mixed up. 36.
6 and 6.
6 and 6. 9 and 4. Anything else? 18 and 2. All sorts of different ways. We'll do 6 and 6. Then we have 2 and 3 and 2 and 3. So we'll circle our leaves down here. So now what we can do the same thing as this if necessary. Eventually you're going to get this visually, but let's write this out. Let's look at our 2's first. We have 2 times 2 times 2 times 3 times 3 times 5. So we have 1, 2, 3 2's, 2 3's, those are accounted for, and then our 5. So now looking at our factors, can we pull anything out off the bench or from the Radicand? The 2's. How many do we pull out?
3.
Okay, which makes up how many teams?
1.
1 team. Very good. So we have 2. And this will end up being what? What is left inside? So we have these 3 together, and that gives us 1 team of 2. We are left with what else?
40?
What's that?
40?
Close. 45, yes. So 3 times 3 is 9, times 5 is 45. Okay? So we are able to simplify 2, because we found 3 2's that are a factor of 360. We found 3 A's and pulled that one out. We found 2 sets of 3 B's, so we got to pull 2 of those out. And what's left over is the 45, A to the second, B to the first. And this is simplified. Now you're thinking, well, I've got 9 times 5. Well, 3 goes into 9 2 times, so I should be able to pull a 3 out, right? Because the square root of 9 is 3. Doesn't that make sense?
No.
So what's wrong with that? Why can't we pull a 3 out?
Because there aren't 3 of them.
Exactly. And this thing, pay attention to this little fella right there. Because you will go through all this stuff and end up making a boneheaded mistake just like that. Oh, well, 3 times 3 is 9. I can factor 3 out. And you put a 3 out there. But you can't, because that fella right there, he's like the coach saying, I've got to have this many people to get out here for this team. But that dictates how many of them. So don't fall into that trap. Don't get so caught up into a problem that you forget what you can and can't do. Okay? Make sense? Awesome. Any questions so far? Let's do... So let's do this. Now we're going to take this same problem we're going to keep all of our factors out here. We have our 360 factored out, our A's factored out, and our B's factored out. Let's take this and turn this this radical form into exponential form. Okay, but factored out. So we'll deal with the number here in just a minute because it's a little bit more complicated and we're just now learning this. So let's get the letters down. So we have A 5/3. Okay. B 7/3. Okay, and let's look at those right now. We have basically an improper fraction as an exponent, right? Okay, can we rename that? Maybe. How? Okay, let's leave those. There are ways to rename that, but let's leave those. Now let's think about the 360. Okay, you could have 360 1/3. You could do that. Okay. More accurately, though, is this to be factored out. We have our 2's, our 3's, and our 5. So let's do it that way. If we have our 2's, how many of them do we have? 3. 3/3. What about our 3's? We have 2, so that's 2/3. And our 5's, we have 1/3. So what about this guy right here? 2 to the power of 3/3. Kind of interesting. Think way back. What is, if you saw just that fraction right there, 3/3, what would you think of?
1.
1. So you'd have 2, right? You could rename that as just 2. What was it whenever we simplified this originally? 2 was on the outside of the radical, right? Because we have 3 of them. So it's simply 2. So what you can do, if necessary, is you can take this 2 and rename it as 2 to the power of 3/3.
Oh, so then B and 7/3 would be B and 1/3? Or does it work?
Yes, you could essentially rewrite this as, so you would have 2 times 3 to the 2/3, 5 to the 1/3. You could do A times A to the 2/3 times b squared times b to the 1/3.
Yeah. So if we did it to the first one, would you have to do it to all of them? Or does it matter?
Depends on what you're trying to accomplish. So yes, if you wanted to. No, if you don't need to, why do the work if it's not necessary? The importance of doing this right here is not necessarily that we want to make things more difficult and we found one way of doing something, so let's try to do another way to do something with it. Renaming is what makes our lives more simple in math. It's already complicated as it is. Why not make it more simple if we get to rename stuff in different forms and use it to help us out? Well, sometimes we need to rename things to help us out. For instance, if we needed to use this 2 somehow, but we had all these exponents that were in fraction form, but we somehow needed to use this, you could rename this as 2 to the 3/3. If all the other ones had denominators of 3 and you wanted to combine that, well, you can rename this all you want to. These are the same thing, same exact thing. Make sense? Or why have it spread out like this whenever you could combine them and make it more simple to where it's just a to the 5/3. And then you get to combine things even more. It just depends on what you need it for. Sound good? We keep finding different ways that we get to rename our statements. And it helps, I can't even just express how much it will be helpful once you get these graphs down and start thinking, well, I can't do this. Well, I can. How do I make it work for me? What do I need to do to make it different so that it will work for me? Okay, everybody has this down? Cool. Alrighty. Now, we're not going to actually write this out, but what this also helps us with is this answers your question that you had earlier. Everybody turn to page 276, and we'll see an example of what you were talking about. It says simplify taking the 4th root of 1024. Well, as you see, it ends up being factored out. It's 2 to the 10th. Well, then to rename that into exponential form, it is 2 to the power of 10/4. Well, to make life easier, you can actually simplify this exponent and change it to 2 to the the power of 5/2. Okay? And then if you needed to, you could do 2 and times 2 to the 1/2. If you needed to do that. I'm sorry, 2 squared, because there's 2 of them that come out. Okay? Different ways of renaming it, but yes, you can even simplify it to make life easier. And that's always helpful. Alrighty? Let's move on. 7.3, sums and differences. All right, sums and differences. What does that mean? What mathematical thing are you going to be doing if you hear the words sum and difference? Yes, addition and subtraction. Sum means to add, difference means to subtract. So we're going to be adding and subtracting radicals. The best way to understand this is think of this in like terms whenever you add and subtract. Can you add x squared plus x plus 1 and end up with 3x squared? No, although sometimes people try that, you cannot do that. Can you add any of these together at all? No, we can't because they are not like terms. They are completely different terms. Radicals are going to be the same way. Again, the best way to understand is to think of them as like terms or not like terms if we can put them together. So, what we will do is look at example number 1 on page 279. Now, just like if you were to add x plus x, that equals 2x. Likewise, in example 1, we have 5, I'll keep that up there, 5 to the square root of 2 plus 6 to the square root of 2 plus the square root of 2. First of all, we have all like terms because it's the same number that is listed as the radicand, the same number that's on the bench, okay? Same number that's on the bench, so already we can identify that they are like terms. If necessary, think of this as, you can even think of it as benches. We got 5 benches, 6 benches, and how many benches? How many benches is this? 1. Another common mistake is this one will completely be discarded because you don't see a number in front, but it's understood that there is a 1 in front of it. So here we have 5 plus 6 plus 1. All that times the square root of 2. So 5 plus 6 is 11 plus 1 is 12. So we end up with 12 benches. 12 times the square root of 2. And that's how we simplify it. Make sense? Now, if we have this, x to the third, square root of 3 plus the square root of 4, can we add those together? No, we cannot add those together. Why?
Not like.
They are not like terms. Very, very good. Even if we change this to square root of 3 plus 2, they're still not like terms. You can't, it would have to stay in this form. Now, it being addition, you can switch it. It's the same as 2 plus the square root, I keep saying square root, the square root of 3. I was right. Man, my brain is like jumping so far ahead right now. Since you're adding, you can flip-flop these and it still says the same thing, but you cannot combine them anymore because they are not like terms. Now, subtraction is the same thing, okay? Addition, subtraction, it's the same thing. You have to have those like terms. Another way to think about it is fractions. Whenever you add or subtract fractions, you have to have a common denominator. You have to have a common denominator. Which means the bottom number is the same. Same thing, the number on the bench is the same. So, let's look at example number 2. 2 to the square root of 8 plus the square root of 12 minus the square root of 32. Are any of these the same, like terms? Before you just up and say no.
They all have something that can be divisible.
Yes, and here the index is saying we're looking for 2. Whenever you don't see something here, it's understood that there's 2. So let's factor these out and see what we have. We start off with 8. We're going to rename these first to see if there's something that we can do with these. So we have 8, so we have 2 and 4, and then 2 and 2. So already we have 2 of the 2s, so we can pull them out as 1, 2. So it would be 2 times 2 times the square root of 2. We took the 2 that came out from here and multiplied it times this 2. Will ultimately give us 4. Now let's look at 12 and see what we have. 12 We have 2 and 6, 2 and 3. So we have some 2's that can come out. And again, they are one, they come out as one team. Now let's look at 32. We have 2 and 16, 2 and 8, 2 and 4, 2 and 2. So we have one pair, another pair, and we have 1, 2 left over. Minus 4 to the square root of 2. Does everybody understand how we got 4? We had 2 teams of 2 that came out as each being one team, so we had 2 sets of 2's that came out. And so we have the 2 times the 2, and that gives us a 4. Now, do we have some like terms that we can combine? Mm-hmm. Yes, we do. This one we cannot. There is only one of these that has a 3 on the bench, but we do find 2 of them that have a 2 on the bench. So 4 square root of 2 plus 2 square root of 3 minus 4 square root of 2 gives us what?
2 square root of 3?
Absolutely, 2 square root of 3. Because when you have something and you take away that exact amount, you no longer have anything. You have 0. So what we're looking for is the similar term, and then we're adding and subtracting the numbers that are out front, the ones that are actually out on the field playing. They got into some sort of violent issue and bad things happen, and they all got kicked out of the tournament or whatever, so they're not there anymore. Red carded for soccer players. What's the card for basketball? Is it blue?
No, you get
You just get ejected?
Yeah.
They just kick you out? Oh.
You have to wrestle them
I know in baseball you kick dirt all over the place.
It's the penalty box for ice hockey.
Yeah.
If life were like ice hockey, like whatever you do bad, 5 minutes in the box, you're fine. Like that'd be so nice.
Yeah, 2 minutes, and then indoor soccer is the same way. You get a blue card, and then you got to be 2 minutes off the field. So.
In a basketball, you just storm off and take your jersey, you untuck your jersey.
And then you drop down and fake an injury. You do that. All right.
Or next to the rim.
Yeah. Let's look at example 4. Example 4. Does anybody have any questions how we renamed these to find like terms?
No.
Okay. As you begin to factor numbers, you will, like 8 gets used a lot, and you know that that's 2 times 2 times 2. So whenever you see an 8 or other numbers, you will use them so much that you won't actually have to factor them out. You'll know what to do with them. However, for right now, I highly suggest that you write out your factors and then circle the leaves, just like whenever you're in pre-algebra, but it will help you tremendously and keep you from making mistakes. Because it's not fair to you to go through all this trouble and come up with an answer only for it to be wrong because you missed one factor. One factor made your answer wrong, and you did everything else correctly but got a wrong answer. You deserve to have that right answer after doing that much work. So take that little extra time and make sure to do it right. All right, we're going to look at example 4. We have 2 times 3 to the power of 51 minus 5 times 7 to the power of 10 plus 3 to the power of 51 plus 2 times 7 to the power of 10. So, can we combine, or can we identify like terms? All right, which ones? Okay, 7 to the power of 10. We see a couple of those, and what else?
No, 3 to the 51.
3 to the power of 51. That's correct. All right, so what we're going to do, this one is a little bit more confusing, and if you we'll wait on that, because I think it's going to be a little more confusing. Let's write it out the way this example does, okay? We have 2 times 3 to the power of 51 and plus another 3 to the power of 51. And that is going to be added to 2 to the power, or 2 times 7 to the power of 10 minus 5 times 7 to the power of 10. So let's group these together, and then we can go on from there. Now here, we're adding the whole numbers that are in front. You have to think of these as being under, like in a bubble, or under the square root sign, or on the bench, okay? These numbers here, they have to stay the same. It's what is out in front of them that matters. Here we're multiplying this one times 2. And this one, there's one of them, so we end up with 3 times 3 to the power of 51. Plus, here we have 2. We're subtracting 5, so we're actually going to be subtracting 3 times 7 to the power of 10. And that will be our final answer with that. So again, this one's a little bit more tricky. It's important that you know it so that you can use it. But again, make sure that you create your bubbles around these. These are your like terms. What's being multiplied is what you will end up adding together. So pay attention to what is out in front of them. Alrighty? Cool. Alright. That's adding and subtracting them. Adding and subtracting. Now let's go to the product. What does product mean?
The end result.
Yeah, what mathematical application is taking place? We just talked about adding and subtracting. What would product be? Multiplication. Very good. We're going to multiply. Everybody say that's good. Multiply. Very good. See, and with enthusiasm too. I appreciate that. That's awesome. Good times. Good times. So just like whenever we were factoring, we can take our factors and go in reverse. So if we had 8 here, since we were talking about 8, and we factor it 2 times 4, 2 times 2, well, we can go in reverse. We can take 2 times 2 times 2 and use 8 if we needed 8. If we needed them factored, we can use it in the factored form. So we can go back and forth as we need to. Likewise, whenever we are multiplying, say, x times y, well, both of these have an index of 2, so we can take that same thing, a radical sign with the index of 2, and just put everything multiplied underneath it together into one term. We've essentially multiplied them together to get to a combined number. Just like here, we're multiplying them, all the 2's together to get a combined number of 8. If we needed to, we could separate them back if we found, like for instance, if we had square root of x times y plus square root of x, well, we could simplify this as square root of x times square root of y plus x, and then that equals what?
Wouldn't it have to be square root of x times y plus x and something? Or no, the x, y, and then have that by itself.
Why can't you add this to this and end up, what's that?
I wasn't doing that.
No, I'm saying why
No.
can't you?
'Cause
I'm saying, let's say I want to. I'm saying I think it should end up being 2 times x plus the square root of y.
This could
Can you do
be
that?
multiplication because the order of operations.
Very good. Absolutely. In fact, that's a great point. The order of operations doesn't allow us to do that. We have to multiply first and then add and subtract. Not to mention, we're multiplying, these are actually combined terms. Okay, you can't just remove one out of there and add it to something else and then mix and match to that extent. Okay, because these are still combined, it's almost like using parentheses, they're attached to each other. You can't just pull one away and start adding. Mindful of that, so be mindful that whenever we add and subtract terms and then even get into multiplying. Does everybody see that? Okay. We'll see more of this. All right. Let's do. Let's do this. Example number 1, 2 to the square root of 50. I need to erase all this. 2 times the square root of 50 times 4 to the square root of 5. What can we do with this? We actually have a couple different things we can do.
So factors of 50 would be 5 times 5. So could equal 2 now?
Okay. So everybody, don't look at your book. Just look at this. What is your first instinct? Because we're multiplying, we're not adding. We are multiplying. So the rules are different whenever we multiply and divide than whenever we add and subtract. When you add and subtract, you have to have like terms in order to be able to combine them. Whenever you are multiplying or dividing, you do not. Okay, you can put them together. So what is your first instinct to do to simplify this or to perform this operation? Close the book, walk away. It's time for a tasty beverage and some Funyuns.
It's time for more stuff.
Yes, more SpongeBob. I know y'all watch SpongeBob. Okay, so raise your hand if the first thing you would do is multiply the 2 times of 4. Okay, so 2 times 4 is 8. We took care of that part. Now what would you do next? Okay, would you keep the radical sign? Okay, so the radical sign, 50 times 5, so 250 is what she says she would come up with. Who else would do something like that? How many of you don't know what you would do? There is absolutely nothing wrong with doing that right there. That is one way of doing it. Okay, and then can we simplify this? Simplifying meaning we want the lowest possible term onside the bench. We want as many people playing out on the field as we can. Okay, so what we can do is take 250 and let's factor it out. I can only assume there would be a 5 and a 50 since we just multiplied, but that's just me, kind of crazy. And then we do 5 and 10, and then 2 and 5. Well, we have 5, a 5, 2 and 5. We can list them out if we want to get a better visual. The index is telling us we need 2. Well, here we have 2 5s. And they come out as 1 5. So then we have 5 times 8. We only have 1 2 and only one more 5. We can combine those together and we have 10. So it gives us 40 to the square root of 10. Okay? So we combined everything together, got one number, and then factored it out from there to get our complete answer of 40 to the square root of 10. That is one way of doing it, and chances are that's how I would do it. Just visually for me, I take everything, put it as small, and then you work it out from there. Other people are a little bit different, okay? You would maybe prefer to work with smaller numbers than having to deal with one big number. So let's do it that way. We're going to go over here. We have 2 square root of 50 times 4 to the square root of 5. 5 is a prime number, so we can't factor that out anymore. But 50 we can. 50, we have 5 and 10, and then 2 and 5. Okay, so let's circle our leaves. We have 2, a 5, and a 5. Our index is telling us we have to have 2. Well, we have 2 5s right here. They'll come out to make 1 5. And we can multiply that out here. So we have 5 times 2 times the square root of 2 times 4 to the square root of 5. Well, this also equals 10, okay? Well, now we can combine them just like what we did in the beginning on this side. So now we can combine 10 times 4 is 40. We multiply the outwards, and then we multiply the innards. So it's 2 times 5. The square root of 2 times the square root of 5 is the square root of 10. So here we come up with the same answer using 2 different methods. Whichever is easiest for you, whichever one you feel really good about yourself, you've expressed yourself completely, and you get to the right answer, it's even more important. So raise your hands if you would do this way. Raise your hand if you would do that way. Oh, double answers. Interesting. Raise your hand if you didn't raise your hand. Okay, we'll go. I know this stuff is really hard, right? If you were to look at it and just try to figure this stuff out, it seems very complicated, but whenever you do this, it's actually pretty easy, and especially whenever you do a couple of them, it's pretty easy. Let's see. We are now, let's do this one, just so we can get an idea of this as well. Don't look at your book. Do not be on page 284 and look at example 4. Don't do that. So we're going to do 2 times the square root of 3, because I bet every one of you can do this without needing your book whatsoever. I think what we've learned so far, you're going to get this down. All right, let's multiply this out. First of all, what property is used to get rid of the parentheses? Distributive. Oh, thank you. That touched me right here. That was awesome. Yes, the distributive property. One of the properties that we use the most throughout these math classes. Okay, so let's go through and distribute this for each one of these 3 terms and figure out what we're going to have. We'll do this together as a class. Yay! So 2 times the square root of 3 times 1. What is that?
2 to the square root of 3.
Thank you for not saying 1, because that would have been incorrect, but some people might have still done that. So we took care of that. Now, the next one, getting a little bit more difficult. We have like terms, so this will be 5 to the square root of 3. Okay? Y'all see that? 5 to the square root of 3. No. Are we adding them?
No.
Multiplying.
We're multiplying them. So no, this is not the right answer. This is a bad, wrong answer. Bad answer.
Oh, okay.
We're multiplying. We multiply this times each one of these terms. Multiply. So we have to multiply this times this, which gives us what?
6 to the square root of 3.
Another common mistake. Good thought. When does the term stay the same? When do they have to stay the same? You don't change them. It's like adding and subtracting fractions.
When it's got a common denominator.
So when we add and subtract these, then those don't change. They stay the
But when
same.
you multiply those.
Absolutely. So when you multiply, you actually multiply everything. So this will be 6 to the square root of
9.
Thank you. I was going to say 6, and I was hoping I'd get that. So yes, it's 9. Now, can this technically be simplified?
Yeah.
Okay, we'll do that in a minute. Okay, let's do this one. So 2 times the square root of 3 times 6 to the square root of 7. Now this is negative. We know that a negative times a positive is going to give us a negative, so let's just go ahead and get rid of that. Well, I say get rid of it. Let's go ahead and put it where it belongs, so we don't have to worry about it anymore. We caught it. Yay, good for us. Let's put it down there. So it's 2 times the square root of 3 times 6 to the square root of 7.
12 to the square root of 21.
Perfect. So 2 times 6, the outwards, 12. Now we multiply the innards. 3 times 7 is 21. Very good. Now, this term right here can be simplified. 6 times the square root of 9, which is what?
3.
This is 3.
No, it's 2 times
So then it would be what?
2 to the square root of 3. What?
Well, 9 factored is 3 and 3. We're looking for 2 of them. So they all come out as one team of 3. So it'll be 2 to the square root of 3 plus 6 times 3, that one team that comes out, 6 times 3, minus 12 to the square root of 21. Okay? And then 6 times 3 is 18, so we'll just rename this as 18.
I'm confused about that.
This one?
Yeah, then you, how did you get that into the 3 times?
So let me ask you this. What is, and this is a really good question because it gets confusing whenever you see other numbers attached. And now that I look at it, I see how my writing is like going at a crazy angle. Apologize. So let's just do this. What is the square root of 9?
3.
3. Well, what do we do with this 6? This is 6 times the square root of 3. So we have this, I'm sorry, the square root of 9. 6 times the square root of 9. Well, the square root of 9 is 3, so it's still 6 times that. It's just renamed.
Because we got rid of
Oh, I
that.
see.
Okay.
Mm-hmm. And so, which helps understand, and this, I can't express this enough. I wish I had impressed this on people sooner, like as in years ago, because I think this impacts a lot. Much of what we're not picking up or we make mistakes on is because we simply read it and we're not understanding what it's saying. What helps us understand is if we say it out loud. 2 times the square root of 3. Oh, I'm multiplying a 2 times the square root of 3. Saying it out loud helps your brain trigger, oh, I get this now. So 6 times the square root of 9. Well, what's the square root of 9? 3. Oh, 6 times 3. and that gives us our 18. And then minus 12 times the square root of 21. But this will be our answer down here. There's nothing more we can combine. There's no more multiplying or dividing taking place. So what's left is adding and subtracting, just like what was brought up earlier. We did our order of operations, which in this sense, we got rid of our parentheses. We did that through multiplying. We multiplied. Now we go to adding and subtracting. We can't combine like terms, so it stays in this format. Does that make sense? Perfect, perfect. Ooh, let's do this one. This is a good one. We're going to do one more, and then that will be it, I think. Yes. Maybe. We'll see. Let's do this one real quick. We may do one more section I want to see. 3 plus the square root of 2 times 5 plus the square root of 3. What does this look like? What method will we use? Yes, the FOIL method. FOIL, see, you say FOIL and everybody's eyes lights up. Yes, FOIL. We're going to use the FOIL method, only we're using radical expressions in order to do this. So let's do our first. 3 times 5 is 15. And then the O is outer, so we'll do 3 times the square root of 3 plus 3 times the square root of 3. Then our inner plus 5 times the square root of 2. And then our last square root of 2 times the square root of 3 is a square root of 5.
Wait.
What?
Wouldn't it be 6?
Yes, thank you. Very, very good. Because we don't add them whenever we're supposed to be multiplying them. So it is actually the square root of 6. 2 times 3. Good eye. Actually, if you want to talk like an Australian, you can say good eye over and over again, but say it fast together. Say it. Say good eye.
Good eye.
Again, together.
Good
fast.
eye.
Good eye.
Good eye.
See?
That's legit how they say it.
Yeah.
It's so cool.
Everybody get it now? Yeah. Okay. Kind of dumb, but whatever. So, now, we use the FOIL method to get here. Can we combine any more terms? Do we see like terms up here? No. This one's a whole number. This one has a 3, this is a 2, this is a 6. It has a 2 and a 3 in it. So this is as far as we're going to go. Okay? Awesome, awesome, awesome. All right, we are going to dive real quickly into 7.5, just because we understand the concept of multiplying product. Now we're going to look at quotient, which means we're going to be looking at fractions or division. So let's look at example number 1, 10 to the square root of 8 over 5 square root of 10. Now, what we can do is we can break this up into 2 pieces to help us if we need to. Okay, some people it may help to do this, others they won't. So we're going to do 2 different ways of doing this over here. What we can do is, I'm going to rewrite it, 10 to the square root of 8, 5 over 5 to the square root of 10. We can split these, okay, to where you have 10 over 5 times the square root of 8 over 10. Does that make sense how we went from here to here? We pulled the whole numbers away and we're working on them, and then we took the radicals and we're working on those. Okay? So then 10 divided by 5 is what? 2. Times the square root of 8 over 10, which is, we can factor out a 2 from both of them, gives us 4/5. And we end up with 2 4/5. Another way of doing this, some people like to simplify where you factor everything out in on top and bottom of one long division sign. Make it one big fraction. And then you go canceling out.
Oh, good on you.
Okay? I'm still going to do it just because it helps people out. But we have 10 is 2 times 5 times the square root of 2 times 2 times 2. All right, and then we have 5 times the square root of 2 times 5. Now in this format, the whole numbers we can factor out. We can get rid of the 5s. And here, everything that's inside the radicals, we can get rid of whatever's there is on top and the same amount on the bottom. What's left over, we group back together. So there's a 2 left. We have 2. And then we have the square root of 2 times 2 is 4. And here is 5. So there is that method if that helps you out to make sure you're not forgetting something. So either one of those ways works. Doesn't matter as long as you get to the right answer and as long as it's making it easier for you. Yes, ma'am.
I have a question.
Mhm.
Okay, so on some of the homework problems, like they have one where it's the square root and then it just has, like for instance, it would just be the square root of 8 over 10, but it has a 3 in the index. What do you do then?
Well, you can, which homework?
It's number 6 on the exercise 1A.
What page?
290,
You said it's number 6.
number 6. How it has a 3 in the index.
Oh,
What
yeah,
would you
yes,
do
I'm sorry.
with the index?
Hold on one second. Let's do, no, good question, because let's go over number 2, the example number 3, I mean, because then we can see how it's actually worked out, because you will have to, I think there's one of those on there. No, I think there's 2 of them. So let's go over example number 3. Very, very good question. All right, so we start off, we're given 2 over 12, but the index is 3. Okay? Now, what we can do is, first of all, we simplify, and then we will end up renaming. So let's simplify this. We're going to kind of work our way over. So we have 3, and it's 1 over 6. Okay? Now, just like before, if you have the square root of x over y, it can be the square root of x over the square root of y. We're going to do the same thing, okay? Now we have the cube root of 1 over the cube root of 6. Now what is the cube root of 1?
1.
Yeah, you keep adding or multiplying 1 no matter how many times together, you're always going to end up with 1. So that will end up being renamed as 1 over cube root of 6. So we have that right there. Make sense so far? Now, what we don't want to do is, and this is where the homework for this is trying to get you to, you don't want, if necessary, a radical on the bottom, okay? Kind of like you don't want a negative exponent on the bottom. So what we want to try to do is get rid of this, rename this whole statement to where it's a whole number on the bottom, which is okay. It's just whatever you do to the bottom, you do to the top. How many of these 6s do you need to pull 1 6 out and have none left over? 3 total, right? So how many do we need to multiply to this one to make that happen?
Wait.
We need 2 more, right? So 2 combined with this one will give us our third. So we can multiply now we're not multiplying 12 times this. Okay, 12 times 12, we're not doing that. because we have to multiply. Remember, if we multiply the 12, we're only multiplying the whole numbers that are on the outside of a radical. So we have to multiply this times the square root of 6 times 6, which is what? 36. But essentially what we're doing is we're multiplying this whole statement times 1. Because the square root of 36 over the square root of 36 is what? 1. But what's missing out of this right now that you see?
The 3 in the index.
The 3 in the index. Everything, in order to put this together, make it work, it all has to be the same. Okay, so now let's do this. We have the cube root of 36, and the cube root of 6 times 6 times, yeesh, that's a bad number. What the heck? That'll be gone. So, which we're going to do that. We're going to rebuke the devil straight off the bench and out there, okay? Because we see 3 of them, and we're going to bring him out, and that's going to end up being a whole number. So then we have the cube root of 36 over 6. And then now we can go on from there. Okay? With that problem, that's the idea, is trying to get rid of that radical from the bottom to where we have a whole number. Again, renaming to help you achieve those things, okay? Any other questions? Awesome job. That concludes this portion. Obviously, you can see why we're breaking this chapter up into 2 parts. Oh, homework assignments. Homework assignments. Yay.